All right, let's dive in. Today we're talking about charts and graphs, and the main thing that's going to be the driving focus for us is different types of graphs and making sure that you are familiar with those, that you can read them, and that you could produce them if you were asked to. The first type of graph we're going to look at is something you're probably very familiar with. It's a bar graph. Bar graphs are used to show data that are in specific categories. And one of the key things about a bar graph, one of the things that make a bar graph different from other graphs that we're going to look at is bar graphs show the raw data. We can see the exact numbers in a bar graph. This is in contrast to like a pie chart that we're going to work on later on, where you can't see the raw data. All you can see are the relative proportions, the percentages, however you might want to phrase that. But in a bar graph, you can see the raw data. We're just going to work with vertical bar graphs. Bar graphs can be made horizontally also, but in general, we're going to work with vertical bar graphs. And when we make a bar graph vertically, that means that the x-axis is going to be our categories and our y-axis is going to be our frequency. Just a little reminder in case x and y-axis are a little fuzzy or a long time ago. The x-axis is the one down here, and the y-axis is the one over here that's vertical. And so when we make bar graphs, the x-axis, this is where our categories are going to go, and the y-axis is where our frequency is going to go. Because of that, what that means then is the taller the bar, the more data points there are in a specific category. So if we have a really tall bar here and a shorter bar here, then that means that category 1 here has a higher frequency, more data points than category 2 did, whatever those categories might be. And like I said, it is certainly possible to make a horizontal bar graph, but we're going to primarily be looking at vertical bar graphs. As we go through this, let me know if you have any questions. My guess is bar graphs are probably pretty comfortable for most of you, but if you have any questions, just let me know. So here's an example of a bar graph. A class of students has the following eye colors. 16 students have brown eyes, 6 students have blue eyes, and 2 students have green eyes. And we've made the corresponding bar graph. Just sort of a brief inspection, you can see that the brown bar is the tallest, and so that is the one with the most data points in it. Blue is next, and green is the smallest. And those are the sort of order of brown has the most, blue has the next most, and green has the least. Remember, a key thing about bar graphs is that we can see the raw data. And what that means is I can see on here that 16 people have brown eyes. I can see that if we draw it all the way over there, we can see that 6 people have blue eyes, and we can see that 2 people have green eyes. And so we can see the raw data right there in our picture. Not all graphs will do that for us. Bar graphs are one that can. One other thing I want to mention about bar graphs is we have these categories down here along the x-axis. Those categories can be put in any order. What I mean by that is, and we'll see an example of this in just a minute, where sometimes what's along that x-axis needs to be in a certain order to make sense. But for a bar graph, we can put those categories wherever they want. Green, brown, blue, they're all very distinct from each other. If you see this graph, you may be a little bit like me and go, why would you put green first? Why wouldn't you make it so it went highest to lowest? Because I would if I saw this graph. And so, okay, we can do that. We can pick the green bar up, put it over here, and then pretend that this one isn't there, or if we were making the graph, just not even put it there to begin with. And you'll notice that the graph gives me the same information. It makes just as much sense if I rearrange them this way. I can put the categories in any order I want. That'll be perfectly fine when we're working with a bar graph and the categories that are along the x-axis. A special type of bar graph, sort of a specific type of bar graph, is called a histogram. You can see at a quick glance that this is a bar graph. We have these vertical bars, and we have categories along the x-axis. We have frequencies along the y-axis. So it meets all the criteria of a bar graph, but it's a special kind of bar graph. In a histogram, the categories on the x-axis are data that need to be arranged in a certain way. Meaning, if this is the hours of life for batteries that were tested, and there's 37 hours, 38, 39, 40, 41, 42. So what we're seeing here in this bar graph is how many batteries lasted a certain number of hours. So as I look at this, I can see that, all right, of the batteries in my test, there were 2 of them that lasted 37 hours. Looks like maybe 4.2 lasted 38 hours, and so on. So I can see here how many hours they lasted. What's important about this to note, what makes it a histogram, there are 2 features. One is that the data down here, 37, 38, 39, 40, 41, 42, it needs to stay in that order to make sense. If I picked up this bar that was 40 and put it on the front, it would be really goofy. It would mess up what this graph is trying to show me. And so we need, because the data is continuous, meaning 37, 38, 39, 40, 41, 42, there are certain numbers associated with it, and it only makes sense to arrange this one way. We can't put the categories in any order we want. We want to make sure they stay this way. Also, when we make a histogram, the data is always shown without any gaps. So you'll notice that these are right next to each other. There's no gaps between the bars. And that's because this data is continuous. There's 37, 38, 39, 40, 41, 42. There's no gaps in my data, and so there's no gaps between my bars. I do want to point out, though, let's say we went up to 43 and there were no batteries in that, and 44 had 1 battery there. Our histogram could look like this, and you might say, well, what about that gap that you've got right there at 43? Technically, there's not a gap. Technically, there's a bar there. It just doesn't have any height. And so if you were to see something like this in a histogram, it doesn't mean there's a gap. In fact, it means the opposite. If it's a histogram, there are no gaps. We have to put 43 on there, and it just has to have a bar with no height. We're not going to spend a lot of time on histograms in section 7.1, but we'll revisit those in section 7.3, and they'll be more important for us there. One of the most important types of graphs that we're going to look at is a line graph. It's important to note that line graphs are best for showing change over time. For example, here we have funds spent on road construction in some fictitious town back in 2010 to 2013. And we can see that they spent a little over 7,500, a little under 15,000, close to 30,000, and then down under 22,500. That's how we'll read the graph. We've got our years down here. And again, notice we want to put these as 2010, 11, 12, 13. We want those to go in a logical, chronological sequence. So we want to make sure we don't put the 2012 all the way on the left. That would make things very hard to read here. And then we have the funds, the amount that was spent on the y-axis. The reason that a line graph is so good for change over time is because what we can see in this graph is when did things increase and when did they decrease? This is tied to the idea that you might remember from algebra class of slope. You might remember there's a formula for calculating slope, and that's great, but we're not going to do that. I just want you to be able to identify a place in here where there's a decrease. So from what year to what year did the funds that were spent decrease? You know what? Before y'all type, well, you can go ahead and type it, Nicole. That's fine. But it occurred to me I could have made a poll for this one. But y'all can go ahead and type it in. Yeah. I changed my mind. Oh, I wasn't fast enough. Very good, Nicole Zochel. That's funny. Yes, the decrease is from 2012 to 2013. You're exactly right. And we can see it's a decrease because it went down. That's it. Don't overthink it. Technically, you could say it has a negative slope, and that would be correct. But really here, it went down, so that's a decrease. And that's between 2012 and 2013, there was a decrease in the amount spent on roads. And then the other two have an increase. From 2010 to 2011, there's an increase. And also from 2011 to 2012, there's an increase. This time I am going to do a poll for this one. I don't think it's a hard question, but I just want to make sure that you're seeing this the way that I need you to see it. Let me type this in. All right, pretty relatively simple poll, but my question to you is this. Over which years was the increase more? Where was there a more significant increase? Where was there a more significant increase? Or, another way to phrase that would be, when did it increase faster? When did it increase more? Any of those ways of phrasing this. When was the increase more significant? And we'll just go 15 more seconds on this one. Where was the increase more? All right, let's take a look at this one and see. Almost unanimous. I kind of expected that this one would be. Let's go back and take a quick peek. So here we have an increase in the first year shown in my graph. From 2010 to 2011, there is an increase because it went up. It went from about 7,500 to about 15,000. So about a 7,500 increase. And then this one, because it is more steep, because it would have a higher slope, if you wanted to say that, because this one is steeper, this is increasing more than the other, or increasing faster than the other, if you wanted to, depending on what the data was. Here it increased more, and it's because it's steeper. It's a sharper incline, so that's where it increased more. The reason that line graphs are great for change over time is because it's easy for us to see these increases, increasing more, and decreases at a quick glance. It's really easy to see what's happening. Is it going up or is it going down? Really easy to see that in a line graph, and that's what makes them best for change over time. Next up, we have pie charts. These are also known as circle graphs. I tend to call them pie charts. You might see them referred to as circle graphs somewhere along the way. And what these are for is to compare different categories similar to what bar graphs did. But on a pie chart, we don't see the raw data. Instead, what we do see are relative proportions and percentages. If we're trying to do percentages, relative proportions, then a pie chart is our best choice. If I want to sort of at a quick glance see how does one compare to the other, a pie chart is a great choice for that. Let's look at an example. We had that eye color data from before where we had 16 students with brown eyes, 6 students with blue eyes, and 2 students with green eyes. If we wanted to make a pie chart for that, we already saw the bar graph, now we'll make a pie chart for this. A really important thing, if we're going to make a pie chart, is to keep in mind that what we're doing here is we are making a circle. And what we're going to do is we're going to take this circle and we are going to cut it up into sections so that each category gets a certain amount of my circle. That's the whole philosophy of making a pie chart. The way we're going to decide how to cut that up is based on the number of degrees there are all the way around a circle. Does anybody remember how many degrees there are if you go all the way around a circle? Excellent, Natalie. Very good, Genesis. Escadar, perfect. There's 360 degrees if we go all the way around the circle. So what we're going to do here to make a pie chart is we're going to decide how many of these degrees am I going to give to brown, how many am I going to give to blue, and how many am I going to give to green. What I wouldn't want to do is say, all right, well, I'm just going to cut this into 3 equal pieces here and make this brown and this blue and this green. That would work if I had the same number of students in each category, but I don't. So I don't want to do that. Instead, I want to make sure that I'm given the appropriate number of degrees to each eye color. So let's take a look then. I have brown eyes. I have 16 students. For blue eyes, I have 6 students. And for green eyes, I have 2 students. And what I want to do is I want to set up a way to make sure I'm giving the appropriate number of degrees to each category. What I'm trying to do here is I want to make sure that I distribute my degrees proportionally. It's an important word, and you'll see why in just a minute if you don't already know. A really important number for me here is going to be the total, if I'm going to make a pie chart. I know the total number of degrees is 360, so I'm going to need the total number of students. And that'll be, let's see, 16 plus 6 plus 2 is 24. Here's how we're going to go finding out how many degrees I should give to each category. You can do this using decimals and percents, but because we were working on proportions last week, and I want to sort of stress the idea of proportionality, we're going to do this with proportions. I also like using proportions here because if we use decimals or percents, we might round early on in the process. And anytime we round early in the process, our answers might not be as accurate as we need them to be. If we use a proportion here, we don't round till we get to the very end, and that's okay. Here's how we're going to set this up. I'm going to set a proportion for brown eyes that says, well, 16 out of 24 students have brown eyes. And I want that to equal, I don't know how many degrees out of 360 I should give to brown. So our philosophy here, remember with proportions, we always want to make sure that it's logical. Thanks for the total number there, Escadar. I just noticed it. We want to make sure our proportion makes sense. It's logical. And here I'm saying 16 have brown eyes out of 24 total. How many degrees to brown eyes out of 360 total? So that's the logic. That's the rationale I'm using to make my proportion. Now we'll solve this by cross multiplying. So we'll cross multiply here and have x times 24 is 16 times 360. Big number, I don't know what it is, but 16 times 360 will be 5,760. One last step to get x by itself. What do I have to do to get x by itself? Just a little refresher from last week. I agree we need to do something with that 24, Escadar and Lysa. What's the operation? Edison, Lorraine, Emily, Genesis, excellent. A whole bunch of divides coming in. Karina, Lysa, very good. Okay, because this is 24 multiplied by x, if I want multiplication to go away, I need to divide by 24 on the left. Those will cancel, and we'll divide by 24 on the right. When we do that, we're left with x on the left-hand side, and then 5,760 divided by 24 is 240 on the right. What we just found out is that x in our equation that we originally set up here is 240, which means we're going to give 240 degrees to brown eyes. We're drawing a pie chart. You might be thinking, how in the heck am I supposed to draw 240 degrees on there? Don't panic. I'm not going to ask you to get out a protractor, but we can ballpark it pretty good. Here's what I mean by that. If we know it's 360 all the way around, then halfway around would be 180, and halfway to there would be 90. And that kind of makes sense to us. A right angle, 90 degrees. Okay, sure. And then let's see. If this much is 90 and this much is 90, then 90 more would be, what would that number be right there? How many degrees would I be over there at 9 o'clock, let's say? What number of degrees needs to go over here as I make my very good, Lorraine, thank you. 270 degrees goes over here. And again, I'm not going to ask you to get out a protractor. We're just going to ballpark this and say, okay, well, I need to give a certain amount of this pie chart to brown eyes. And so drawing lines from here, I go from my starting point, which is 0. 0 and 360 degrees would be in the same place. And I start from 0, and I just need to go around until I get to 240. And I can kind of ballpark that as about right here. And there's 240 degrees. And what I've done then is I said that this part of my pie chart represents brown eyes. Those 240 degrees are given to brown eyes. If I want to know how many degrees I'm supposed to give to blue eyes, I'm going to do the exact same process. All right, well, let's see here. It looks like for blue eyes, 6 out of 24 students have blue eyes. So 6 out of 24 students have blue eyes. How many out of those 360 degrees should I give to blue eyes? And we're going to go through the exact same process of setting up and solving a proportion. We've got our proportion. 6 have blue eyes out of 24 total. How many degrees to blue eyes out of 360 total? We'll cross multiply, have 24 times x is whatever 6 times 360 is, 2,160. And then just like last time, I've got 24 multiplied by x. If I want multiplication to go away, I'll need to divide by 24 on the left. Those will cancel. If we divide by 24 on the left, we also divide by 24 on the right. On the left-hand side, all that's left is the x. On the right-hand side, 2,160 divided by 24 is 90. And so I just found out that 90 degrees is going to be given to blue. Here comes a really important part, something that can be a little bit sticky for students sometimes. So I'm going to give 90 degrees. 90 degrees goes to blue. Your instinct might be, well, 90 degrees, that's right here. I'm going to draw that in and call this blue. Why is that no good? And there's a lot of reasons you could give, but one of them is probably more obvious than the others. There's a lot of things you could say here and be correct. It's cutting into the brown. Excellent, Nicole. I like that very much. It overlaps the brown. Perfect, Lorraine. Very good, Edison. There are no students in this class that have both blue eyes and brown eyes, so we don't want to have a part of our pie chart show that. So essentially what you guys are telling me is all this has already been given away. We can't use that anymore. If I want to give 90 degrees to blue, I need to start here at 240 and go from there. So if I want to give 90 degrees to blue, I need to start at 240 and go 90 degrees from there, and that'll put me at 330. There's another way you could draw this, and Lorraine, you might be suggesting it, and yes, I agree with you, Lorraine. I'll do it both ways. So 240 and 90 puts me at 330, and so I can draw a line here at 330. And now I can say that this part is given to blue. How many degrees did that leave me for green? Right here. How many degrees are left? Very good. Edison, Nicole, Escadar, outstanding. So I've given 30 degrees to green. I feel pretty good about that, but you know what? I'm going to go check and make sure. I'm going to go ahead and set up a proportion for green. It will be 2 out of 24 students have green eyes. How many degrees out of 360 should that be? Just to verify that 30 is the right thing here. We'll cross multiply. 24x is 2 times 360, 720. Divide both sides by 24, and we'll have 720 divided by 24. Sure enough, that's 30. So I feel great about my 30 degrees to green. And we've made a pie chart. I do want to go back and address what Lorraine mentioned because I think it's excellent. But first, when we talk about making a pie chart, there are a couple of different ways that I can ask you these questions. I can't ask you to draw a pie chart because I don't have a way of having you do that for me. So there are two different ways that I can ask questions here. One way would be to say, here is our data for this particular situation, and then give you a few different pie charts to pick from to identify the one that's correct. Sort of a multiple choice situation. Here's several different pie charts. Which one is the correct one? That would be one way to go. Then another way would be, and honestly, this is my favorite. Another way to ask these is to say, here is our data. If you were going to make a pie chart for this, how many degrees would you give to brown? And then you would just need to use this process, figure out how many degrees you would give to brown, and then your answer is just 240 degrees. And from there, as the instructor, my assumption is if you can do this correctly for brown, you'd be able to do it correctly for blue and green as well, because it's the same process. So those are the two different ways I can ask you a pie chart type of question. Which one of these pie charts is correct for the given data? Or how many degrees would you give to a certain category? Now I'm going to back up for a minute and talk about what Lorraine mentioned. So we're going through the process of, we've already figured out how many degrees to give to brown, and we've drawn that. And then we decided, okay, how many degrees am I going to give to blue? And we do our calculation and we see, hey, it's 90 degrees. There's absolutely nothing wrong with starting at 240, going 90 from there and putting it at 330. That makes perfect sense. It's a good way to go. But another way to go, if you happen to notice what Lorraine did, is, well, 90 degrees is pretty easy for me to draw if I've got this vertical line already right here, and I put this horizontal line right here. That's a 90-degree angle. So I can just do 90 degrees from here to here, from 270 to 360. And if I have 90 degrees there, and I call this the blue part, of my pie chart. Then I can put the green part right here. Same information as before. Green still gets 30 degrees just like it did before. It was just an easier way to draw it. It was excellent for Lorraine to notice that and to bring it up. I want you guys to say stuff when it comes to your mind for the next 14 weeks. But I also want to point out here that just like with a bar graph, it doesn't matter what order we put these in. A lot of times, pie charts will be made going from biggest, then blue, then green, to go biggest to smallest, but it doesn't matter. You can put them in whichever order you want. And here, the brown went first, and now the green second, and the blue's third. Totally fine. You'll notice, when we looked at the bar graph, we could see the raw data. When we looked at the bar graph, we could see that brown has 16, blue has 6, green has 2. We can see that in that picture. Oops. In the pie chart, though, we can't see that. We don't see any of the raw data here. So if we want raw data to be shown, we'll use the bar graph. If instead we want a quick comparison to be made, like, in this one, I can see at a quick glance, brown's more than half, blue's a fourth. I can make those quick comparisons. I can see relative proportions, and I can see not exact percentages, but kind of. I can see that brown is definitely more than 50%. Blue is 25%. It's 1/4 of it. I can see those relative proportions and percentages are what I can see in a pie chart. If we go back and look at our bar graph, I can see that brown has the most and green has the least, but I can't really see at a quick glance that brown's more than half and blue's 1/4. So if I want relative percentages, relative proportions, that's where a pie chart comes in. All right, I want to have you do a pie chart question for practice. Data was collected on people's favorite meal of the day. 6 people said breakfast, 10 said lunch, and 14 said dinner. If you were going to make a pie chart for this, what number of degrees should be given to dinner? I'll make a poll for this, and you can tell me that way. And we don't have to be in a hurry for this at all. We're actually getting close to the end of class today because there's not that much content in 7.1. It's a nice section to group with 5.1 because we're doing proportions here in the pie charts. We did proportions last week. And so we don't have to be in a hurry on this one because we don't have much time left. We'll go another 30 seconds on this and then talk about it. All right, let's see where we are. Not unanimous, but pretty close. Definitely strong agreement here. Let's take a look at it. So our favorite meal data that we have been given lets us know that breakfast was the preference of 6 people, lunch was the preference of 10, and dinner was the preference of 14. A really important number for us anytime we're making a pie chart is the total. So let's see, 6 plus 10 plus 14, that's 30. And so we have 30 total. Now, we could go through the entire process of making a pie chart and realizing that there are 360 degrees all the way around the pie chart. I'm starting at 0, and I'm going to give a certain number of degrees to breakfast, and then lunch, and then dinner, and finish my pie chart. But this didn't ask me to do that. You'll see problems in the homework that will ask you to do that. But this just said what number of degrees should be given to dinner. So we don't have to go through the whole process of making a pie chart. Instead, we just need to figure out what number of degrees are going to be given to dinner. And so dinner has 14 out of the 30 people. So there are 14 out of the 30 people that prefer dinner. How many out of the 360 degrees then should I give to that category? That's what we're trying to find out here. And so we use a proportion to do that. And to solve this proportion, we'll cross multiply and have 30 times x is equal to whatever 14 times 360 is, 5,040. And then because it's 30 multiplied by x, we're going to divide by 30 to get x by itself. And if we do that on the left, we have to do that on the right. On the left-hand side, those 30s cancel, leaving just the x. And on the right-hand side, 5,040 divided by 30 is 168 degrees. So we're going to give 168 degrees to dinner. And we've answered the question. That's it. If we were drawing the pie chart, we would just say, all right, well then, I know 180 is down here, so 168 is going to be somewhere over here. And then that would be the dinner section. And we can continue on to figure out how many degrees should be given to breakfast and lunch and finish making our pie chart. But since this question just said what number of degrees should be given to dinner, that's our answer, and we're all done. Does anybody have questions about that they want to ask before we sort of do a little bit of a summary and wrap things up for today? Awesome. Fantastic. All right. In addition to understanding how to create and read bar graphs, line graphs, pie charts, one of the types of questions you'll definitely encounter will involve which type of graph is best. Or in your homework, what you're going to see is, critique the use of this graph for this particular data set. Essentially what they're saying is, did the author of this graph use the right choice? I want to mention something about the homework also before we wrap up, but I'll get to that in a minute. Just as sort of a review here, bar graphs are great for showing raw data, and those categories that are on the bottom, they can be arranged in any order. Main thing, if I want to see raw data, bar graph is a really good choice. A histogram is a special kind of bar graph. So it's kind of a subset of a bar graph because it really is. It's just a special kind because the data is continuous. There's no gaps between the bars. We'll revisit this again in section 7.3. They're not going to be really important for us in this section, but I do want you to know they're out there and they exist so that when we get to 7.3 and I mention a histogram, you already know what I'm talking about. Line graphs have a very specific purpose. change over time. If I want to see where things are increasing and decreasing over time, a line graph is the choice. And then finally, pie charts are great for showing relative percentages. If I want to be able to see that something's more than half or right at 1/4 or any sort of relative comparison between two things other than one's taller than the other, bar graph can show me one has more than the other, but a pie chart can really show me those percentages in a better way. So in that case, a pie chart is a really good choice. I mentioned the homework. One thing I want to mention is like on page 352, the homework that's for section 7.1, what you're going to see there in your assigned problems is, especially when you get over to like anything that's between 15 and 26, any of the problems in that range, the instructions for parts A, B, and C are down at the bottom of the column in between problems 14 and 15. So A, B, and C, for each of these problems, the instructions for those are between problem 14 and 15. It's kind of strange, but it's one of those things where what the instructions say are, for exercises 15 to 26, do these things. And part A is describe something that you can conclude from the graph. Part C is critique the choice of the graph. And so that's why you'll see parts A and C in your homework for those questions. Parts B, we'll kind of get to that. We'll get to that when we talk on Thursday about reliability and validity.